Yeah, and last but not least, today we're talking about feature extraction from time series. So yeah, remember that of course we can also extract features from some complex data representation in order to get a standard representation like feature vectors. So the traditional way to extract features from complex objects. So instead of directly working with the entire time series, of course we can extract some features from them, so transfer them into some feature space, so to say. Yeah, but with time series, since typically time series per se are kind of feature vectors, especially if the values that we record over time are real valued, then of course they are time series of length n is an n-dimensional feature vector. So in the context of time series, feature extraction basically follow two different purposes. The second one here is the original purpose of feature extraction, where we usually want to model specific properties of the objects we are working on. So in this case, it's of course time series we are working on. So specific properties of time series that are relevant to a given application. And we'll cover an example here, but just one example, because as you may imagine, there are so many applications that demand specific feature extraction procedures or features. So feature extraction is always extremely application driven. So in this case, only just one example at the end of this subsection. And the other purpose here is that we aim at representing time series in a more compact way than the original ones. So for example, a shorter approximation of the original time series, in the best case with a minimum loss of a modeling error. So it's a more or less a dimensionality reduction technique for time series. But now we can, of course, make use of the periodic nature or the sequential nature of the time series. Yeah, and this is of course mostly done for performance reasons. Also for easing up the curse of dimensionality. So the approach is closely related to dimensionality reduction, feature selection, and we will cover a lot of examples here. The most probably popular examples here, which are discrete Fourier transformation, discrete wavelet transformation, should be dVt, not dTv, and singular value decomposition, which we already know from the high dimensional data lecture, APCA, PAA, and PLA. Yeah, so let's have a look at those compact representations first. Yeah, once again, we start with the first one here. This is the major part of our section because typically people just apply some kind of dimensionality reduction to the time series and then apply one of those similarity measures we talked about before. Yeah, only if your application is very specific and demands very specific properties from time series, then you have to really come up with a different feature selection process. As I said before, we will cover one at the end today. So anyway, what kind of compact representations we want to cover? So first of all, the aim here is to find a more compact representation. Basically, it's a kind of dimensionality reduction. So we want to reduce the length of the time series, of the original time series, without losing too much information. So upsampling, downsampling, especially downsampling, could be an approach, but of course there's a kind of, very bold approach, just sampling points, but which would actually be the same like just sampling dimensions from high dimensional feature vectors. So the question is, can we make use of the sequential nature of those time series? And of course we can. So the general approach is that we represent time series by a combination of base functions. Yeah? And the different versions or the different methods basically vary in the type of base functions they use. Yeah, so Fourier uses cosine and sinus curves. Wavelet uses wavelet curves. Singular value decomposition takes the eigenwaves. APCA is a kind of looks similar to the wavelet, but is a piecewise mean approximation, typically adaptive. PAA is non-adaptive, and PLA uses some kind of regression functions, piecewise regression functions. Piecewise linear approximation is PLA. So this is the overview. The basic idea is always the same. We use a combination of base functions of some given type, so to say, to represent the time series. So the first approach we will cover all of those. So the first one will be the discrete Fourier transformation, DFT. And as I said before, we use as base functions periodical base functions, sinus and cosine. And the whole thing will be a weighted sum of those base functions with varying frequency. And here is an example. So this is the time series here, the original time series here. And if you use, for example, 3 sinus x, you have this one, or you have this one here. And if you apply plus 1 sinus 3 times x, it gets this one here, plus again 0.8 times sinus 5x, you get this one here, and so on and so on. Yeah? So a linear combination or weighted sum, this is a weighted sum of those 3 base functions, in this case only sinus functions. You can approximate this one here as a weighted sum of those base functions. That's the basic idea, basically. Yeah? And Fourier's theorem says that any periodic function can be represented by a sum of sinus and cosine functions of different frequencies. Okay, that's a good story. That's a good point. Yeah, so let's try to do that. So the discrete Fourier transformation originally finds a different equivalent representation in terms of it just transfers the original time series of length n into another representation which has also n coefficients, but now the coefficients are the weights of the cosine and sine sinus functions. Yeah, so DFT transforms a time series of length n into n complex numbers, with frequencies f such that the original time series, or the transformed time series, I'm sorry, each point of the transformed or time slot, so to say, of the or dimensions of the new time series. Yeah, so this is those are n numbers, complex numbers, xf, and each complex number has this determination where we have a real part and an imaginary part, as you know from complex numbers, of course. Yeah, and you see here that it's a weighted combination of cosine and sinus. Yeah, and a weighted sum actually. Yeah, and of course j is so j squared is -1, the imaginary part. Yeah, and so the real part is the portion of cosine in the frequencies, where the imaginary part obviously is the portion of sinus. Yeah, of sinus. Yeah, so you have the cosine part and the sinus part, that's how you can compute that for a given time series. So what's the interpretation? Actually, DFT can be interpreted as a transformation of basis vectors, pretty much like PCA, for example, yeah, but in a different way, of course. So the new basis is spanned by the frequencies, which we have here. Yeah. So this is the original time series, which has n dimensions. Each dimension, each time slot, so to say, is one dimension. So time slot 0 is the first dimension, time slot 1 is the second dimension, and so on and so on. And the DFT transforms that into a new feature space and the dimensions are the frequencies. Yeah. So the question is, why does that help? Yeah. So far we just transformed an n-dimensional time series into an n-dimensional vector. Yeah. So the DFT also gives you n frequencies out of n time slots. So what's the point here? Yeah? We wanted to have a more compact representation, and now we don't gain anything because we have an n-dimensional representation and here again an n-dimensional representation. So what is the point here? Yeah. Okay, so wait a minute. First of all, it holds that the Euclidean distance is preserved after the transformation. So the Euclidean distance in the time space is the same as in the frequency space. Yeah? And this follows from one specific mathematical theorem, which is known as the Parseval theorem, and also the linearity of the transformation, of the Fourier transformation. So the energy of a sequence, which is the sum of squared amplitudes, is preserved by the discrete value Fourier transformation. That is actually Parseval's theorem. So this is Parseval's theorem. And from this, it follows that, of course, well, if the energy, the sum of the squared amplitudes is preserved, then obviously also the Euclidean distance is preserved. Yeah. So once again, what does it help? Well, now comes the important trick. In practice, the low frequencies, so that are the first components, have the highest impact on the modeling error, so to say, or on the sum of the squared amplitudes. Yeah, on the amplitudes, so to say. So it contains the most information, and that is pretty much similar to the first principal components computed by PCA. Yeah, so we can use the same trick as PCA, but now with discrete Fourier transformation. So focusing just on the first C coefficients is a good choice if we want to reduce the dimensionality of a sequence and make a minimum of loss in the amplitude spectrum. Yeah, and since we have the equality or the preservation of the Euclidean distance, using only C components instead of n yields even a lower bound approximation of the Euclidean distance in the original space, which can be used by some algorithms to also safely prune things, objects from consideration, from patterns, yeah, from computing specific patterns. Yeah, and this approximation will be better when using just C coefficients computed from the discrete Fourier transformation instead of just sampling C original timestamps. Yeah? So that is the idea, just like PCA. Yeah? So PCA also is the idea that we compute the principal components and then take a subset of the n principal components because we know that those are optimal with respect to variation. And here the first the first coefficients are optimal with respect to the amplitude spectrum. Yeah? So that is the basic idea of DFT, and that's why people use it pretty much, yeah? pretty often.